I hope everyone had a nice lunch break. I hear there's a really good Egyptian food truck around. For those of you who went, yeah, was it good, Charles? Okay, I'll check it out tomorrow, I guess. Okay, so it's time for our second keynote. So today we have Marion Marschalek. I assume a lot of you are probably familiar with Marion's work from her numerous Black Hat and Hacker Conference talks and also trainings. Marion organizes reverse engineering trainings. She has a lot of experience in malware reverse engineering. If you look her up, you will find all these nice articles and presentations and whatnot. So Marion used to work at Intel and AWS. More recently, she started her own company called Hack and Cheese. Check it out; it's cool stuff. And I'll let you.
Thank you. Awesome. Microphone is working, slides are working. That's the basics we need. Hello, my name is Marion. I'm a reverse engineer. And I'm here today to talk about the last 15 years. And why 15 years? It's because I've been in this industry for 15 years. And like the last 15 years, I was really obsessed with binaries. And I'm telling you, obsessed enough to tattoo binary code on my arm. So that happened. I started out as a reverse engineer in the malware industry, that is big, the antivirus industry. Back in 2011, and naturally things have changed in those last 15 years. From malware analysis, I went into incident response, which really just means do malware analysis faster. From incident response, I went into offensive security and started a job at Intel, where I looked into microarchitectural vulnerabilities. More specifically, I had the opportunity to write a exploit for a microcode bug, which was very instructive in learning how the Intel architecture works. For me, like specifically as a reverse engineer, working for Intel was like joining the mothership, if you will. And I learned a lot about how the actual instructions work that as a reverse engineer, you usually just get to look at. I got to look into those instructions. So that was awesome. And yeah, as Christoph just mentioned, after Intel, I went to AWS to do large-scale threat detection, specifically focused on Linux malware. So there's been this strain of binary analysis through my entire career. And it's interesting, when I got the invite for the keynote here, the organizers asked me what I was going to talk about. And my answer was basically like everything. I don't have a specific topic that I think would be interesting enough for you guys, except all the little peculiarities I've encountered throughout my career. And yeah, the problems back in the day looked different than the problems we have now. Like back in the day, we didn't have working tools. Now we have too many tools. They all have different features, and those different features are a bit of a challenge. Now we have different problems. Like back in the day, specifically if you looked into malware, you saw Visual Studio compiled C code executables. And that is important to mention because the first couple of years of my reverse engineering career, that was all I saw. And I thought that CDECL was all that there was. And it turns out nowadays we have so many different other ways to build binaries. We have so many calling conventions. We have binaries that show different types of calling conventions because compilers can decide whatever they want to put into those executables. And that has made the space so much more exciting. Also, at the beginning of my career, I started with malware. Now I am back in the malware space. I am now winning my bread by teaching other people how to reverse engineer malware. And I specifically went back to look at malware. Because in that space, like looking at all the things I've done, I have learned the most. Which seems weird. Like if you ask people about malware, there isn't that much going on, right? Except that there is. Like throughout that, those adventures that I was going through over the years, I had to deal with the Visual Studio compiled C programs, then there was C++, suddenly there was Visual Basic 6, then there was .NET, now we have Go, then we have Rust, now we have malware that runs on IoT devices, we have malware that runs on edgeware, we have, to this day I haven't a good definition of what edgeware really means, I'll tell you that too, but we have malware that's running pretty much on everything that can execute code. And that has made the space attractive again. Okay, so that's why I'm focusing on malware. But not just malware is hard, like binary analysis altogether is hard. That has a list of reasons. The first one up there is lack of tools, and I just told you that we have so many tools now at our disposal. You have to imagine when I started reverse engineering, the first tool I ever touched was OllyDebug. How many people in the room have used OllyDebug in the past? Okay, how many of you have seen soft ice before? There's still a few hands, awesome. Yeah, that was back in the day when tools were still good, and I'll get back to that topic in a few minutes. Nowadays, we have so many different frameworks, like not just the tool, but entire frameworks full of tools and features that help us reverse engineer. And they are good. If you look back 15 years, they were not good. Like we had tools, we had frameworks with features, and there were so many bugs in there. Like back in the day, something like function recognition in a perfectly well-compiled C executable was a problem. Like just to find out where the function starts and ends, which you can imagine is important if you want to look at call graphs and control flow and all of these nice things that we want to extract from binaries. If you don't know where the function ends, that basically gets very hard. And back in the day, we still had issues with that. Nowadays, we do not. So the tools have moved along, and like many other features were added, and now the tools don't crash as much anymore, which is also nice. That's with the tools. We have these big frameworks now with all the different features, and they're still not enough. And I'll also be talking about what the problems there are. Yeah, and then there's all these other different reasons of why binary analysis is hard. If you've ever seen like a 50 megabyte big C++ executable, you have to take a deep breath and like go back into that binary and then face your fears, because that is difficult to analyze. And as you can imagine, that is where automated binary analysis gets really interesting. Then there's such topics like binary protection obfuscation. I'll be showing some examples of what that means too, where essentially I am of the opinion everything's possible to reverse engineer, but you really cannot do static analysis on code that doesn't represent the original functionality of that code. That is a big problem that we're looking at in the malware space. And that is just like if malware authors intentionally try to make things hard. Then there's compilers that do not intentionally try to make things hard, but just by their nature make things harder. And I'll be also speaking about Go and Rust executables in that light. Then, of course, we have varying operating systems. There's different versions of libraries that make known code recognition difficult. There's obscure system features. One of those would be BPF and BPF bytecode, which I'll be talking about later. And then, of course, one of the big challenges is specialty skills. And I think a lot of people in the room are working on automated binary analysis, which is to ease that problem with needing specialty skills. I'm a reverse engineering trainer, and I can tell you from my experience, it is not possible to train enough reverse engineers to analyze all the binaries that need analyzing. Yeah, that's why what you guys are working on is really cool. And what do we do about all these problems? Some of us do research, and some of us do engineering. And one of the big points of my talk today is that there is a gap. There's a lot of people doing research. That research gets published and then never touched again. There's a lot of people doing engineering, and they're working on problems. It's just not entirely proven that the problems they're working on are the right problems. The reason for that is we have a lot of tooling. There's an entire market that is trying to sell you products that solve the problems that you have at hand. But then there's also so many objectives. And I'll also be talking about a bit how hard it is for the people who build the tooling to follow all those different objectives that binaries these days pose. And about the tooling, I mentioned I'm looking at 15 years of my own experience. That's pretty much all I can talk about. But then I started digging, and I realized that the tools that we're using are pretty much twice as old as that. And very interesting for me, I dug up a blog post from the Hextrace developers. In 2020, they celebrated their 30-year existence. So right now, we're looking at 36 years of Hextrace and 36 years of IDA Pro. The first line of code of IDA Pro was written in 1990. I was 3. And that just shows me how in depth these topics go. The one thing I can say about IDA, I have a long-standing love-hate relationship with them, and that is not to say I truly appreciate Hexrays. And IDA Pro is probably the best reverse engineering tool that we have today, save for Google. And that within is because they have developed that product for such a long time. They have also dominated the market for a long time. Back in, when was that? 2016, I wanted to automatically extract call graphs from executables, and like that requires you to script a tool, right, to get that automation going and get your data. And back then, scripting IDA Pro meant that you had to run your script in the context of a GUI, because you couldn't run the IDA Pro disassembler disattached from the GUI. And so back then, when you were scripting IDA Pro, you ran your IDA Python script. IDA Python was supported at the time already, thank God. You ran your IDA Python script in the context of the GUI, which means like you automated that in a bash script and then saw the GUI pop up every time IDA Pro ran the disassembler binary. 2016, like it's not that long ago, right? Nowadays we have tools where we can run scripts headless, as they call it, like without the GUI, and that's great, and IDA Pro supports it now too. What was needed for IDA Pro to get there, evidently, is market pressure. Market pressure was only built up when other tools entered this market, and surprisingly so, that didn't happen until, what, 2019? We'll get there. Yeah, and IDA initially was developed because there was a need for interactive tools. If you can think of a non-interactive disassembler, the only one these days I can think of is object dump. We really just get the disassembly, but you cannot change it. Preparing for this talk, the only bit of research I have actually done was I reached out to the different developers of the frameworks that we have and asked them different questions. And if you have ever talked to Hexrays, you might have gotten a response from a person named Ilfak or a person named Igor. For a long time, that was the company. And to my questions, I talked to Ilfak, and he's not a man of many words. When asked what's their coolest feature, he said the decompiler, which is great. I have never actually seen the decompiler because I can't afford their license. And more interestingly, the feature that was the hardest to implement, he mentioned undo. Have you guys ever used the undo feature in IDA Pro? It appeared one day, there was the undo feature. You have no idea, there was like a drama that went back at least 10 years where people mentioned like IDA Pro is an editor where you edit a database, right? You're not actually editing the executable, but the IDB, which is their representation. And there is no way to undo a change that they made to the IDB, which shouldn't be that hard. But apparently implementing that feature was one of the most difficult features that Hexrays ever had to implement. Now we have an undo button, and apparently people aren't actually using it, which is disappointing, you guys. Yeah, and then IDA licensing. IDA licensing has also gotten an update. Now we have different versions, including a free version, which is very nice. And I'll be talking about that in a bit, a little more. And then to close that chapter, here's a screenshot of IDA Pro from 1991. Let's just say they made some progress. Then, the other tool entered the market in 2019, developed since 1999. Here we have Ghidra. Ghidra offers a lot of the same features that IDA Pro has, right? We have the disassembly. The disassembly quality is actually very good. I've compared the different disassemblers a while back, and Ghidra and IDA Pro are very comparable in that aspect. They're also open source, which means it's possible to adapt the tool, and that also makes the tool free, which I think is why the market adapted to it so quickly, because IDA Pro licenses are very expensive. It was the first de facto competitor for IDA Pro, which is a bit sad, given it was only released in 2019. And the one unbeatable feature is it comes with a free decompiler, which was great from the analysis perspective. Then we have Binary Ninja now too. That was released in 2016, although honestly, I hadn't heard of Binary Ninja until at least 2019. I think they started out rather slow. They started out as a CTF project, like development of the tooling actually started much sooner than 2016, but 2016 they went to the market. They were focused on API from the get-go, like automating binary analysis was one of Vector35's big goals when they developed that tool. And you can see that in their API, it's actually very accessible and even well documented. Also, they're very proud of their graph view and their decompiler. More so because they integrated the graph view with the decompiler and with all the different intermediate representations that they have, of which there is a lot. There is a whole choice of what they call intermediate languages. And I know that many people in the room will appreciate that a lot. I also have to admit I haven't worked with decompilers a ton in my life. And I had this interesting conversation with Fish Orange, and I know that he's really into decompilers. And I had to think about why I'm not a decompiler person. The reason is that I've seen so many binaries in the malware space who were not to be trusted, even if you looked at the instructions. And we'll look at that in a second when we talk about obfuscation. Anyway, what Binary Ninja is really proud of is, again, the integration of GraphView with any intermediate language that you have. And I find that really helpful. Like, binary analysis tools adopting graph representations was one of the best features they had ever done. Because looking at text-based disassembly takes so much more time than looking at the graph of a function. And now if you have decompiled code in the graph of a function, you can only imagine how much that speeds up the analysis. So that is awesome. All right. Number 4 in the big framework selection, there is Radari 2. How many people in the room actively use Radari 2? There is hands. That is exciting. It is wonderful. It's one of my favorite projects in that field. I also have to say I don't actually actively use it in projects because I need to be fast. And to date, I have not managed to remember all of the command line instructions that I need to actually disassemble and analyze the binary. Anywho, this project was established in 2006, so it's also been around for a long time. And there is a lot of features. Not all of these features work at all times. I have tried to build as mentioned, I was looking into automated call graph extraction. And since IDA Pro was basically not scriptable in an automated way back then, I used Radari 2, which is great. Like, it's very approachable in a scripting manner. There's so many scripting languages that you can use with that framework. It is insane. The problem that I ran into was that there were so many bugs that held me up. Like, I tried to use a feature, found a bug, reported it to Pancake. His name up here, his name is Sergio Alvarez, but he goes under the handle Pancake online. And at the time, they had a Telegram group, so I just texted in the Telegram group, and a couple of minutes later, I would get a reply from Pancake who said, it's fixed, like, go fetch the next commit. And I fetched the commit, and the bug was fixed. And then I kept going and found the next bug and went back to the Telegram group, and we played that for a couple months. So that was long back and forth, and like, as this process went on, they added new bugs, and like, as I pulled the latest commit, I got a fresh bug into an API that I thought was already fixed. And so that was a lengthy process. Radari 2, for the longest time, I believe, has been developed by one person. It is not per se a product. It is more of a hobby project, but the depth to which the analysis goes and the amount of features that have been integrated into Radari 2 over time are just sheer impressive. And it moves extremely fast. I just saw, like, you request a fix, and the fix is there within minutes. You request a feature, and like, if Pancake is interested in that feature will land in the project within hours. It is impressive. He might be one of the best reverse engineers I've ever met, because he has solved so many problems over the years. And I'll get back to solving problems in a bit as well. That's why I call Radari 2 the innovator. There's so many features in there, I won't go into details because the list is simply so long. But the one that I probably find the most impressive is you have a WASM build, a WebAssembly build, that allows you to run Radari 2 inside your browser. And that is amazing. Also, there's one feature that lets you color the disassembly rainbow. Then finally, I had this one slide of this one rabbit hole that went down. I'm sorry, I have ADD really bad, but I couldn't skip that topic. It basically doesn't fit in the presentation. Not long ago, I looked at 32-bit compiled Linux malware, and I realized there is so many push instruction in that binary, so many move instructions in that binary, it almost looked obfuscated. And then I realized it's just how they implemented the calling convention. So GCC with 32-bit Intel will spit out CDECL calling convention, but doesn't push arguments on the stack in order, but uses moves to move those arguments onto the stack, which is confusing if you look at it for the first time because it's not in order. Like, it doesn't have to be, right? It can be out of order. And anyhow, I talked to a friend about this, and he said the only thing that could make it worse is AT&T annotation. And I agree, AT&T annotation should just not exist. But that essentially brought me to the question of, like, why do we have that annotation to begin with? If you ever notice, like, there's Intel assembly that has the Intel annotation, and then there's the AT&T annotation. Like, why in the world would AT&T come up with a different annotation? And it turns out that annotation has existed since the 1970s, when Unix developers at the time employed at Bell Labs developed tools for Unix to analyze binaries, back then developed for PDP-11 assembly. I have no idea what PDP-11 is, by the way. But that's how these tools came into existence. And that annotation was simply ported to Intel disassembly as processes moved along. And that's why we have that annotation. And that simply blows my mind. Anywho, the hard thing about tooling. So I just introduced all those different frameworks to you. There are so many tools out there. There are so many more, and I'm sorry I didn't have enough slides to present all of them. And they all face approximately similar problems. So like OllyDebug and SoftICE, unfortunately, both met the same end of life. They're no more being developed. I don't know if you can still use them. They probably don't run anymore on modern operating systems. And that is, well, I haven't talked to those people. I don't know why they stopped developing, but I assume it's for the same two reasons. Developing a reverse engineering tooling is extremely tricky. Like, it's highly skilled knowledge. I will talk about a few of the problems that these people face in a minute. You really need to understand well how all the different compilers produce all the different binaries if you want to bring a product to the market that can analyze the umbrella concept of binaries. So it's a very tricky development. And then it's a difficult market. If you try to get a foothold in this industry, you're basically selling to a few hundred people. That within is also why IDA Pro initially had these like really expensive licenses, because they had a lot of development effort, but then they didn't have a lot of people to sell to. And then they had a lot of people cracking their software, so that was a problem too. But like, essentially the market that you're trying to target is difficult. And I believe that that's why OllyDebug and SoftICE gave up. Now, what does it mean to develop products? And at this point, I'll apologize. I spent 4 years at Amazon, and building products is all they do. And talking about minimum viable products and shipping deadlines is all they do. So that's why that slide had to come in here. Also, people have actually written books about building products, and I only have this one meager slide. But it talks about some of the problems that tool developers face. And in this regard, we're not only talking about commercial tools. So yes, if you want to sell your disassembly framework to people, you have to have a roadmap, and you have to prioritize features depending on how many customers want that feature, and you need to allocate resources. That's a wonderful term to saying we need people to actually do the work. You need people who think about user interface designs and people who do testing and then ship the product, right? Again, I had lunch, I had the opportunity to have lunch with Fish, and I asked him about Anger and where in that space that falls. It's not product, right? You don't go buying open source reverse engineering tools. But then how do they build new features? How do they know what to do next? In the case of Radari 2, it's probably what Pancake wants to do next, right? So there's a different type of roadmap planning, but like if you have a user base that uses your tool, you still have some guiding light of what problem you need to tackle next. And then you fall somewhere into this process. Not every product needs to follow these different steps. But every product that wants to sell to customers needs to have some thought about prioritization of features, how to build those, how to test them, and then how to ship them, how to market them. And one big point that the Hextrace developers brought up with me was the risk of breaking existing customer workflows. If you build a reverse engineering tool specifically, if you're looking at automation of binary analysis, and you add a feature that breaks half of the pipelines that people have set up to use your tool to do analysis with, your customers are not going to be happy with you. And for some reason, that was a risk with the undo button, although I still don't understand what the complexity there was. All right. How many people have seen the Ship It parrot? Nobody? One person? Okay. Like at Amazon, everything you ship, every feature, every line of code you ship gets a Ship It parrot. That's why I have the Ship It parrot. I'm damaged, I swear. All right. The difficulty of selling reverse engineering products to software crackers. Here's a map of 2006 that ILFAC put together in a slide deck from 2014, where they showed their problem with the product they're selling. Their customers mostly are like malware analysts and exploit developers, vulnerability researchers, and people who try to crack software. And apparently having a license check is not a big problem for those folk. That's why at the time they had a huge issue with pirated versions of IDA Pro. That, and something I don't quite understand, they had licenses that were standalone. Like there was no check of a license, whether the license is in the right place, right? Like as soon as you had the license file, you could install the software. And I don't know if you guys ever knew, but like back in I want to say 2013, 2014, some malware running in some analysis box of some antivirus company managed to extract their IDA Pro license. That license ended up on the internet, and then hundreds and hundreds of us were using that license to run IDA Pro because it was essentially free. And that's the problem with standalone licenses. If they don't check back to a server, if they're running on the right machine, and that might have contributed to that graphic. No, it might not, because 2006 is too soon. But anyway, you see what their problem was. And nowadays, it's still not that easy to get an IDA Pro license. I don't know if you ever bought one. Like you had to send them a copy of your ID, and it goes through some background check. And that's an improvement, because a couple of years ago, you couldn't actually go to Hextrace to buy a license. You had to go through a reseller in your respective country, and they would run a check on you before they would actually sell you a license. It was miserable. Yeah, situation has much improved. Also now we have so many features that we used to live without, and I mentioned the graph view is a big change. Then we have undo buttons, which I haven't been before. We have a feature called library recognition, which isn't working entirely, and I'll be talking about that too. And we have a feature that can actually patch a program from out of IDA Pro specifically. Like as mentioned, you have the IDB, right? But that doesn't patch the program if you patch the IDB, and then you need an extra feature in IDA Pro to actually write to the file on disk. And it seems ludicrous today that that had to be implemented, but that was one of those features that landed on the Hextrace roadmap and eventually made it into the product, and it took years. And anyway, everything else, every other feature they have in their products is a similar challenge. And so yeah, we have all these different features, and that makes us very happy, but also we still have so many reasons why tooling fails. And this is really just a list of topics that I have in the rest of my slides. Some binaries don't want to be analyzed. Some compilers really make our lives hard. Some obscure system features really make this harder. And then there are simple things that we still just can't get right. And the lack of maintenance, like as mentioned, some tools just meet their end of life because the developers find jobs that pay actual money and then give up on the tool. And that's unfortunately just how it goes. All right, anyway, binary protections. I keep having conversations with people who tell me that the malware space is a solved space, and like there isn't any more tooling needed there because we have them all, and any more features needed. And I have this one screenshot from a bot that I was looking at a long time ago. which essentially breaks all these assumptions. Obfuscation, there's many different ways of obfuscation, right? And I wouldn't be surprised if somebody in the room knows way more about obfuscation than me. I don't really mind obfuscation so much, as long as I can still read the code. But obfuscation, like binary protection, essentially, what it wants to do is thwart the analysis tools. You can't use a decompiler if the decompiler can't understand the assembly that's underneath. You can't use a disassembler if the code that you're looking at is not possible to be disassembled. And in that sense, this is one of my favorite tricks to thwart the disassembler and every analysis tool that builds upon the disassembler. If you can confuse the disassembler, like how are you going to do automated code analysis? And you guys probably have answers. Like I'm curious to hear. But for me, that is a conundrum. And here what you see on the slide is essentially a jump on itself. As you might know, on Intel, the Intel CPU doesn't really care so much about the disassembly. It just cares about whether it can execute the instructions. And so like if you look at that first jump, there's a jump that jumps from the current position plus 5 bytes ahead, which is the last byte of the actual instruction itself. And there is half the instruction that the CPU will execute next. So as you go disassembling through that code, at some point you see the jump instruction and then garbage. And then if you start disassembling at that target of the jump instruction again, you see an inc instruction that comes after, but the jump instruction disappears. And that is just beautiful. These are gadgets. Like there's compiler plugins that insert these gadgets into code that's output by the compiler. And by definition, a disassembler can't show 2 instructions at the same time, right? Like most of them, at least, are not able to do that. And that's just one example. Here's another one. This is, I don't even know what this technique is called. It's just awful to look at. On a beautiful big flow graph. And then, of course, we have runtime packers. Unfortunately, I can't go into too much depth. I love runtime packers. Obfuscation runtime packers are like my favorite thing. They're beautiful pieces of technology. And they're completely ineligible for static analysis tools because the code that you want to analyze is simply not there at the time of disassembly. All you see might be a disassembler stub. And then usually what we see in those binaries is like these stacks of bytes that are just not analyzable in themselves because they're compressed code. Yeah, that's an issue. A different issue that shouldn't be a problem, the library code conundrum. And I keep talking to people about that, believe me. And people keep telling me that it's a solved problem. And I mentioned that a minute ago and that it's not really solved. Before I came here, I built a Hello World executable and compiled it statically against libc and stripped it and threw it into the different disassembly frameworks that we have. And they simply don't find libc in there. We have library code detection. IDA Pro uses flirt signatures, and Ghidra uses function ID, and I don't know what it's called in Binja. They have that. They do try to find library code. They're just not particularly good on Linux. The feature was initially developed, I believe, for Windows executables, and they are better on Windows. But that specific feature actually degraded over the last 15 years. So when I started looking at my first Visual Studio compiled C executables, library code recognition was relatively good, and nowadays it is not. The reason why that problem is there is probably because there isn't enough money in library code recognition. I can only speculate at what the problem is these days, but it's simply not working. People have solutions. I have my own solution. Other people have other solutions. There's papers about that problem out there. There's open source solutions. There's people who have provided signatures, like prepared signatures that you can run against your executables. It still didn't solve the problem. And that gets me back to building products. Like, if this issue doesn't land on the roadmaps of Binary Ninja, Ghidra, or IDA Pro, it will remain an unsolved problem. And as a reverse engineer, I can tell you, like, it is world-changing to have symbols for library code versus not having those symbols. I have spent so much time in my life reverse engineering libc code. I can recognize certain libc functions by the flow graph of their functions. It is that bad. And that should simply not be a problem anymore. That was that. then I promised obscure system features. BPF is not that obscure, right? It's been in the Linux kernel for I don't even know how long. It's been there for a while. And I only learned about that feature because malware started using it. And that gets me back to what I love so much about malware. Like, I learn a lot about operating systems by simply looking at binaries that try to do obscure things. Like, the more they try to hide, the more I learn about what the system can do. And one of those cases was a malware called BPF door. It's a very simple backdoor that essentially looks for commands from a remote server through a bytecode filter that's installed on the socket. So they inject this very bytecode to a socket to filter for packets. And the issue that I found there was that as advanced as our analysis tools are, they can disassemble a lot of assembly. They cannot yet disassemble BPF bytecode. Specifically, either Pro and Binary Ninja do not have that as a feature in their stock. And so in that case, what I needed to do was get the bytecode out of the binary and then run it through something called Capstone. Capstone is a disassembler that, for one reason or other, already supports BPF bytecode and can disassemble that code. However, an issue there is that they disassemble most of it, but there are certain instructions that are simply not implemented. I have no idea why. I didn't take the time to talk to them. It's just an interesting problem. The lines that you see written in black in the disassembly, the LDXB instruction, that is one that you can't disassemble. So in order to get this disassembly, I patched those out of the byte stream, ran the disassembler over NOPS, and then manually patched that instruction back into the stream, which is upsetting, right? But tooling is tooling, and that's why I said we have so many tools, but not yet enough. Interestingly then, though, Ghidra can disassemble that stuff too, as I recently learned, and they have the same problem with that same instruction. I also had to manually patch that instruction so that Ghidra could disassemble through that, but they then offer a decompiler for that bytecode, and that's a real advancement. From that decompiler, we run into the next issue that to understand that code, you need to understand what a BPF filter can do, and that gets us to network packets, and I have very little understanding of network packets. So I ran that code through an LLM, and I got to this conclusion. Now, whether we trust that analysis or not is a different question, but it sounds like, from looking at the code, it looks like the LLM did a good job there, and suddenly we know exactly what that filter is looking for. We're looking for IPv4, IPv6 packets, and we're looking for traffic on ports 80 and 443, which is web traffic, 22, I think that's SSH, right? Maybe. And yeah, UDP, HTTP traffic, etc., etc. Now we have that information, and we understand what the filter is doing. But that's like an obscure system, and again, building products, if the market doesn't really need that feature, there isn't enough customers that need that feature. Like, why would the binary frameworks support it? Except then we have a malware that infects Linux servers, and we can't understand what it does because we can't disassemble it by code. Time, 20 minutes. The new kids on the block. These days, people talk a lot about Rust and Go. The first time I opened a Go binary in a disassembler, I thought that somebody had vomited GitHub on the screen, because it just so happens that Go builds against its entire runtime, just like Rust does, and that makes for very big binaries with a lot of boilerplate code, which does not necessarily need analysis. Go fortunately ships with something called Go PCL and tab, where it hides symbols and the symbols can be recovered. I mean, we're getting there in a minute. But the thing that most people forget in the light of Go and Rust reverse engineering problems is that these were not the first binaries that were that problematic. How many of you have seen Delphi in a disassembler? A few hands? Awesome. How did you feel about that? People laugh? Okay, thank God. In 2017, I was sitting in a room with 4 other analysts, and I wasn't new to the field, but I hadn't seen a ton at the time. And then our manager entered the room and said, we have a new customer. They want us to analyze a binary and see whether there's a backdoor hidden in that executable. And people got excited because that wasn't malware, that was something different. And then he casually mentioned it's a Delphi application, and there is no source code, of course, and then people's moods just dropped. I had no idea what was going on because I hadn't seen Delphi before, but everybody else just like tried to hide under their tables. And then when we started looking at the binary, I understood why. Delphi is also one of those languages that ships with its runtime built into the executable. And you see like this extra layer of Delphi between the actual application code and the system level. Like, I don't know if you can call it system level code. Like, you would see system calls and system functions that are being called. And Delphi is just like sitting in between. And so if you don't understand the Delphi layer, you essentially had no chance of understanding the application layer about that. That was the challenge there. And then there's Visual Basic 6 P code. I do not believe that Visual Basic 6 had actual application in the industry, right? Like, people wrote applications in that like a long, long time ago. And then it sort of disappeared. And then malware authors, we're talking about like 2015, like a long time ago too, malware authors realized that building something in Visual Basic 6 P code or pseudocode as opposed to natively generates the strange bytecode which is then executed by the Visual Basic 6 virtual machine. And I'll get there too in a second. It is not pretty. First, let's get back to Go. I just put this graphic up there pretty much because it's pretty. If you look at the Go function prologue, it is so much more involved, so much more intricate than what you would see in a regular C or C++ function. And there's a lot going on in there. And yeah, as a human analyst, you look at that and you recognize that it's repetitive code, and then you skip that and look at the actual functionality that's happening in the function. But I can tell you, the first time I looked at that, I was like, what the hell is going on? We're dynamically allocating stack as we go? That is different. An almost bigger problem, though, is how Go stores strings. And that gets me back to the analysis tooling that we have nowadays. And we're talking really about 2026. If you open a Go or a Rust binary in a disassembler, you get the strings delivered to you. Right? There is a pointer that's used somewhere, and there's this comment, as you can see on the screen up there, that shows you the string that is being referenced. I have a feeling the first time Go executables came out and somebody at Hexrace opened those binaries, they were shocked. Because they had to have a new feature in their disassembler that could parse those strings. Because they're not null terminated, they are stored as structures. Go strings are like quite literally just this big whopper of strings that are not separated by anything. They're just identified by a struct that says this offset and this many characters makes a string. That also makes those binaries a lot bigger, right? Like handling any character stream means that we have to have both the offset and the length. Fast forward a couple months, suddenly there's a feature that helps IDA Pro understand those strings, and Binary Ninja and Ghidra, I believe, did the same thing, and the Rust has the same problem. And last year, this time around, Rust wasn't correctly parsed yet in IDA Pro, and then I opened the Rust application again last December, and suddenly the strings look beautiful. It gets me back to the feature development, right? Somebody recognizes a problem, and then there's prioritization again, and we have to find a resource, etc. That's how that goes. Visual Basic 6 P code. What a weird thing to do. Thanks, Microsoft. Visual Basic 6 can be built into native code, which means you get wonderful x86 instructions that represent the application, or you can compile it into P code, which is then bytecode that is interpreted by the Visual Basic 6 virtual machine. And that's what you see abstractly depicted in the graphic here. We have the bytecode on top, and then there's this list of handlers, and each handler then executes the functionality of a given bytecode. It is a very abstract depiction of a virtual machine, but that's how you can imagine that. And when you try to disassemble those files, all you really see is that bytecode, which doesn't tell you anything. I also hear that these applications lend themselves wonderfully to be decompiled. because essentially you analyze all the handlers once, and then you can decompile all the bytecodes that come along, which is why compiled Java code is not a big issue anymore, right? We have good decompilers for that problem. The challenge there, I imagine, is that we had 800 instructions in that bytecode stream. And anyway, in 2014, for sure, there was no good decompiler for Visual Basic 6, because like Visual Basic 6, I don't even know how old that is as a language. I think it's older than me, potentially. And the reason why we need decompilers for Visual Basic 6 Pico, like I think in 2014, still like today, is mostly because of malware, if there's still malware built in that language. Which again, it's a small market. That's why features move slow. Finally, the last example I have on that list is the React Native runtime. That's a very recent example. Something I picked up on LinkedIn was Pancake mentioning that he just implemented a feature for Radari 2 that now can parse overlapping strings in React Native runtime binaries. Which is, you just saw, like in Go and Rust, you have these structures that have a string and a length, and apparently the compiler that builds React Native binaries goes further in where they sort the strings based on the characters, how they start, and then try to build overlapping string storage. So that, like, if you have create as a string and create file as a string, that would be one string, and you would just have the same offset and different lengths. Now try to tell a disassembler how to display those strings correctly in a binary. I imagine that's a challenge. And why do we have so many problematic things in binaries? Binaries come from somewhere, right? We have compilers like, but let's say, entire build chains that create those executables. More specifically, a compiler will take source code and translate it to binary code using many different rules. And among the important influence factors is the application binary interface of the system we're compiling for, and specific restrictions that the CPU has on the instruction set that we're building for. So those are the two big factors that compilers have to take into account. That matters because, as just mentioned, compilers are the ones who create those weird string formats that we then have to build features for the disassembly frameworks, etc. They also dictate how other data types are stored, how vtables are laid out, how exception handling is implemented, etc., etc. And then sometimes the compiler is the actual problem next to all these disassembler or analysis problems that I was just talking about. And more about that in a second. A brief overview of how binaries are made. What I understood this morning is that lots of people here like decompilers. I really like compilers. I had this amazing opportunity at Intel to write prototypes for compiler mitigations. So I had 1.5 years to spend on GCC. GCC itself is not a beautiful code base, I'll tell you that too. There's a reason why research mostly works with LLVM. But it was a very instructive experience. There is different components that have to run to actually produce an executable, and the compiler is really just a small part of it. We have the compiler, the assembler, the linker, and the loader. And the loader includes a runtime linker on Linux. So there's many different components. And they're all very interesting research avenues, and I won't go into details here now, unfortunately. But as I mentioned, one of the important things that the compiler needs to take into account is the application binary interface. And if you've never read an application binary interface specification, they are so interesting. I mean, they're really dry to read, because they're usually a lot of text, really long, and they really just specify how things need to look like. But they explain in such a level of detail how a specific feature of a binary needs to be implemented in the executable. Because compiler developers take those specifications and based on those, then build the compiler that produces the output. And one that I can recommend that I recently involuntarily spent a lot of time in is the Itanium C++ ABI that is used for Linux C++ executables. It is fantastic. One thing that that ABI defines is something called a calling convention. I'm sure everybody in the room has heard about calling conventions before. I don't know if I'm the only one, but there is this one specific one, the System 5 calling convention for 64-bit Linux executables. They use registers to hand arguments over to functions, which is something I have reverse engineered Linux binaries for a very long time. I still can't remember the order of registers that's used for those instructions. If you have a similar problem, there is now a solution. The online platform Compiler Explorer is selling swag, and they have coffee mugs that list exactly that order of registers. I have one of those mugs. It is life-saving. Anyhow, the calling convention is really just a good example of what the ABI defines. So if you look at that, there is certain registers that have a purpose in the call, and there are certain registers that do not. That is defined in that convention. Then there's also rules that the CPU itself has for the use of registers and how instructions need to behave. And if you want to know how that works, there's something called the Intel manual. The Intel manual is so many thousands of pages of book. I forgot how many thousands. It is thousands. And there is one, I believe it is book 3. I forgot the number. But there's a book that documents all the different instructions that are publicly documented by Intel. Each instruction has a tiny little pseudocode section. I don't know if it's still fair to say that most people will never see Intel microcode in person. I think that assumption still holds. However, you don't really need the microcode if you have the pseudocode of how an instruction is implemented. That's why I can just recommend looking at those pseudocodes. And here on the slide, you see the pseudocode for the loop instruction on Intel. So if you ever were curious how one specific instruction makes different decisions, that is all written down in that manual. And again, that's what compiler developers use to figure out which instruction to use to solve a given problem as they build binaries. And as I'm talking about instructions, there's one more thing that I wanted to mention. I'm almost done, actually. Have you all heard of the Mobfuscator? It is a beautiful project. I talked about obfuscation earlier. Like, I should have mentioned this project first. There's nothing like a binary that has one single instruction. A researcher named Stephen Dolan proved in 2013 in a very extensive paper that move alone is Turing complete, that you can show any form of computation alone by the use of move on an Intel platform. So far, so good. A couple years later, Chris Thomas said, what a challenge, and set out to write a compiler that builds binaries that only run on the move instruction. And there is a stack of move instructions here that shows certain operations. I cannot tell you for the life of me what exactly they do. I believe I'm incapable of reverse engineering this instruction flow. And actually, if you look through the presentation that Chris did at Recon back then in 2015, he has entire slides full of applications that have been built by the compiler that are only move instructions. He managed to build branches in move and additions and subtractions. He managed to build interrupts like an int80 only with move instructions. He managed to build loops with a move. And as such, he built I think it was a computer game that he compiled that now is running only on move instructions. The beauty of Intel doesn't end. One more thing I found recently on the internet that also really doesn't fit into this presentation, but I thought it deserves a slide. Somebody wrote a CPU emulator in CSS style sheets. I don't know how, I haven't looked at the code, but that's apparently a thing too now. And you can check that out at lyra.horse. Beautiful project. Finally, the last topic for today. I mentioned that sometimes compilers are the problem. And there is this esoteric field of bugs, which are optimization vulnerabilities. And I wouldn't have touched that topic hadn't I been in an OffensiveCon presentation last year where a Google Project Zero researcher just casually dropped that in his exploit chain, he used a bug that wouldn't have been there had the compiler not optimized away certain pieces of code. And I just got really interested in I mean, he didn't really make a big fuss out of it, and I was like, what? Compiler bugs exist? And I started looking and like, yes, compiler optimization vulnerabilities are a thing. The most famous one happened in 2008, where in OpenSSL memset was removed by the compiler, and memset there should have been used to erase secrets from memory. It just turns out that for a compiler, an operation that doesn't have a data dependency after is really useless. And that's why these memsets were removed. Furthermore, there was an interesting removal of stack protectors by Clang, which just so happens if you put your mitigation in before certain optimizers run, it might happen that the optimizer takes those away. I ran into that issue myself when I was building prototypes for mitigations, which is why most of the work that I'd done in GCC was in the very, very last stages of the compilation process, because I didn't want to go and modify all the optimizer stages in between. If you put your mitigation in early enough in the compilation process, you need to make sure that compilation steps that come after don't remove the things that you have inserted into the binary. And that can be a very, very long and difficult process. Yeah, and then there were other vulnerabilities. For some of them, it's actually really hard to get the specifics of what went wrong in the compiler, and I do wonder why. Anyhow, there is these problems, and there isn't too few of them either. I thought that they're really, really rare, but they actually do happen, and I don't think there's a lot of research going into this area of like how, like I say this, I have no idea whether people have written very many papers on that subject, but if we put code into the compiler, are we sure that it comes out on the other end unscathed? Because we have very, very aggressive optimizers that run over that code and remove things, like they're there to remove things. And there isn't really a guarantee that they're not going to remove the thing that we need in the code to keep it secure. And here's the example that I mentioned from OffensiveCon, a wonderful talk by Ivan Fratrich, who just as part of his chain casually mentioned that a check that should have been there had been removed by a compiler. He had a user of the free vulnerability and needed a info-leak vulnerability, and he was transforming that bug into exactly the thing that he needed. And therefore, he needed to replace one element with a different element with less attributes. So that was the goal. He did so by putting the element into the list through this function called getSaveAttrNameAt, and it worked. And he didn't think much about it until he looked at the source code of that function and saw that that should not have worked because there is a check in there. If you see there the if apos bigger or equal attrCount, that is the check that should have prevented his vulnerability from working. And he got really confused until he realized that that check exists in the source code, but not in the binary. And then the big question arose of like, why? Where did the check go? Turns out the compiler decided it's undefined behavior, and that's how it removed it. There was a bounce check that returns a null pointer. If you look there, like return null pointer. And the problem in itself was that the function it returned to didn't have a check for a null pointer. It expected the pointer to come back from that function and then went on to dereferentiate that pointer without any further checks. The compiler saw that and saw a potential null pointer dereferentiation, did not produce a warning, but decided to simply remove that check because there were no data dependencies on that check. Right, nobody needs that, so let's just remove that. And that's how the check got removed from the output binary. And that was last year, so compilers are clearly still not in a state where they can be completely trusted. All right, almost over time. The AI existential crisis, that's the last thing I'll be talking about. I'm a reverse engineer and I teach other people how to reverse engineer. And I have this existential crisis that my job is going to go away because people keep building better automation in the analysis space and suddenly people don't need to learn how to reverse engineer anymore. That is an issue, and like it's already out there, right? You upload a sample to VirusTool and you get this automated report of exactly what the sample does. Sometimes they're right, sometimes they're not, but like if this gets any better, then like malware analysis will go away entirely, and that is really sad. let me skip forward 2 slides, because reverse engineering in itself is a learning process. I love to reverse engineer because it teaches me how the system works, and I mentioned that about the peculiar features that you sometimes encounter, the obfuscations, the things that you need to figure out. And my big issue, like, don't get me wrong, automated analysis is great and AI is the future, but what worries me there is that over time, I will forget how to read binaries, I will forget how to read code. And naturally, I don't want that to happen. Anyway, I have no good solution for this problem other than I keep teaching people how to reverse engineer, and hopefully this beautiful skill will live through the AI existential crisis. Okay, quick summary if you're interested, and that was my talk. Thank you so very much for your attention. Thanks for staying awake, everybody. I know it's after lunch break.
Hi, awesome talk. I wanted to know if you had any kind of insight of what you think the future is of dealing with a lot of these edge cases you kind of showed off in binary analysis. So I am a person who loves decompilers as well. And you showed a lot of these cases, right, where there's specific instances where you can't disassemble, or there's specific instances where we have a type of packing that hide the code. You know, many of these cases, which we think is kind of like many corner cases. So I want to know if you feel there's a generic approach in this space to get rid of these corner cases at scale, any kind of insight you feel is in that area.
It's interesting that you bring that up. Again, I had this discussion with Fisher Wallinger with solved problems that aren't really solved. Like library code detection is my favorite problem because there's really no reason why it's not working. Packers and obfuscation is a different issue, but there is solutions, and you guys probably know that better than me. There are stacks of papers about automated unpacking and deobfuscation and so on and so forth. There is a gap between research and engineering. Like that's kind of the point of this talk, was to show we have all these problems and there is solutions. Like it's not like we don't know what to do about it, but then there is roadmaps and prioritizations and resource allocation. And so like, if we build automation tools on top of a different tool, and the quality of that analysis tool is really important, right? If your disassembler doesn't produce the right disassembly and the right function boundaries, then you can get a call graph and a control flow graph, et cetera. And so like, in engineering, like in research, a problem might be solved. In engineering, we need to go back and improve the tool that's underneath that we think has already solved the problem. Like Rust is a funny creature. Rust doesn't have a continuous ABI. Like they have an ABI per compiler version, I believe. How they do that is a mystery to me. But so if they tomorrow decide to have a different calling convention, and the disassemblers need to catch up, and the decompilers, I imagine, as well. And so like, it's not like more research. It's probably not gonna solve that issue, but the engineering side of that needs to catch up. And the engineering side hinges on money. Like if there's funding to allocate resources, then yes, we can implement that feature. And in that sense, I think we're improving because there's so much more money in binary analysis now than there was 10 years ago.
And you think that will kind of like stay consistent with this new age of AI-based reversing?
Honestly, I'm not sure that AI reverse engineering without the human in the loop is ever gonna really work, because compilers keep changing and programming languages keep changing and there's new optimization, etc. So like, I don't have a good answer of whether AI is gonna be any better at solving this problem than we are. I just don't think it will.
Thank you.
Thank you.
Hi, thank you for your presentation. I'm Simone Onzo from the Eurocom Research Institute. Really great talk. And mine is more an observation than a question. I would like to know if you share the same feeling, because nowadays when I have to face a binary, especially, malware, there is no more average. We just have extremes. Either the binary is something that we have the tools to reverse, and then now it's extremely easy, or either you don't know you have an extremely complex runtime environment, compile the .NET installer or whatever, then if the tool fails, then you're done. It becomes extremely, extremely difficult. What's your take on that?
More research, more engineering. That's why I mentioned I like malware so much, not because malware in itself is so interesting, it's because of all the research and engineering problems that are in the space. And one thing we can trust is that malware authors will always find the next problem, right? I recently looked at a piece of Linux malware that honestly I don't know how to analyze. They have sort of an runtime packer where they unpack parts of the executable at runtime and then recrypt it, which is not a new technique. But for decrypting, they use an RSA encryption scheme. So you need the RSA private key to actually run the malware. How did you come? That's not, you can't, right? And that's an extreme, but if people find these dependencies for the executable to actually show its behavior and what's in there, we need to come up with new measures of how to analyze the binaries.
Okay, thanks.
Thank you.
Hi, Marion. I'm Lorenzo from UCL. I wonder a little bit, what is your take on source code analysis versus binary analysis? And think about vulnerability. Think about the current state of AI-driven vulnerability analysis and vulnerability research. We have big players, OpenAI coming up, Anthropic, Aardvark, Isle, all of these guys that are getting into the market quite predominantly with their AI solutions to analyze large code bases. But then you also mentioned earlier about this optimization that script away a check. And therefore I wonder, should we be investing more energy on binary analysis, AI-driven binary analysis to find vulnerabilities, also from an industry perspective, alongside with all the effort that people have been doing on source code analysis? So what is your take? Because it seems that sometimes people say, well, there's a lot of open source software, so they're going to go after it. We know recently Isle, I guess, went out with a bunch of new vulnerabilities on OpenSSL that hadn't been checked for a while. But I wonder, when you compile, when using your specific context, many of these things might actually look a little bit different. So what is your take?
That's an interesting question. Yeah, well, the short answer would be we should do both. But there is bugs that exist in the binary that aren't visible in the source code, the compilers are a good example. But also, I think there's entire bug classes that aren't easily visible statically altogether. If there's runtime dependencies or coordination issues between different applications that interact with each other. And I'm not a professional in vulnerability research, unfortunately, but I specifically know the compiler bugs, you can't see them in the source code, so where else are you going to go? And if you're asking how the future should look like, I personally like the binary research better than the source code. Because if I look at, take C++ for instance, if I look at the C++ application in the disassembler, I understand the application quicker than if I look at the source code. And granted, that might be a me problem, but there's things that you see in the binary, like connections that exist, that in the source code are not obviously very difficult to find. And as such, yeah, back to the short answer, both.
Yeah, thanks. Makes sense. Thank you.
Thank you.
Thanks, Marion, for this very nice keynote. I just have one question. Let's assume, just for the sake of the discussion, that you were going to start a PhD in the fall. What topic would you tackle first?
Man, I didn't expect that question. You mean if I can pick and choose? I think I'd pick the compiler bugs, honestly. It seems graspable to represent the code as it flows through the compiler in these different stages and see what happens to the code and verify on the way what disappears and what doesn't. And I did that once, like at a side project at Intel, I looked whether memset instructions were disappearing. So we built the Linux kernel with GCC, and through the compilation process, I was counting the memsets during the compilation stages. And naturally, they became less and less throughout that compilation. And at the time, I didn't find a bug that was specific to a crypto function in the kernel that would not memset 0 a secret. But if you apply that to like your average home-cooked cryptographic application, I believe that you would find things. Anyway, I'm super interested in anything to do with compilers. All right, if there's no more questions, thank you so much for your attention.